Welcome students, welcome to the next session of structural analysis 2. So in the previous class we have started stiffness matrix method for the analysis of the structure. There we have given our step-by-step procedure for developing any structure or analyzing any structure for the supportments or the support reactions or what are the unknowns. Okay, so those unknowns we are using and using the matrix method. In that we have went for the stiffness matrix method and simply a single revision of the step-by-step process. Firstly, we should have to calculate the kinematic indeterminacy or the degree of freedom of the structure, and then we should have to give the coordinate numbers in the for the unknowns, and then we should have to fully restrain the structure in all the directions, and then due to those restrained structure, what are the forces developed at the coordinates we will calculate, and then we will develop the stiffness matrix by applying a unit displacement at the coordinate directions, and finally for such type of view we will generate the equation and the corresponding forces, the forces which are at the various coordinate directions are the final forces which is P, and using the formula K into delta is equal to P minus PL, where the stiffness matrix, load force vector and force vector due to the loads. So using all these things, the delta, the stiffness matrix can be evaluated, and using the stiffness matrix, and then we will go into the member force calculation. So once you know the stiffness matrix, each individual member force also we can calculate it. So I am going into a numerical which is having a highest number of 2 unknowns only. Okay. So analyze the continuous beam shown in the figure by the displacement method. See here, particularly they may not mention flexibility method. So flexibility method is for the force method. Stiffness matrix method is for the displacement method. Please remember repeatedly: flexibility, force, displacement, stiffness. Okay. So force method or the flexibility method is that method. Stiffness matrix method or the displacement matrix method is this method. Okay. Displacement. Okay. So here a continuous beam having A is fixed and having a UDL of 60 kN per meter over 4 meter length up to B, and then from B to C there is 3 meter length, and it is having a 100 kN point load of 1.5 meter from the right end, that is at 3 meters. So what we should have to do? I should have to find the degree of static independence, degree of kinematic independence. The degree of kinematic independence or the degree of freedom we have got as a 2, and the unknown displacements in the problem are the rotation at B and the rotation at C. How much quantity of rotation possible at B? Because see here, there is no horizontal or vertical displacement. There is no rotation. Here, being a support, it will not allow any vertical displacement, but it will give some rotation. And also support C, it will not give any vertical displacement, but it will give some rotation. So what are the quantities of the rotations possible at the support B and C are the main degrees of freedom, because in that way only it is having freedom. Here no freedom is there. Here only one freedom is there, that is in the form of rotation. Here also one freedom is there, that is in the form of rotation. Okay. So in the rotation at B and rotation at C are the possible displacements. Hence the coordinates selected are as shown in the figure. So for the given figure indicating the selected coordinates. Okay. At 1, so this is a clockwise rotation, and C also clockwise rotation, like that I have given. No problem, we can give in the reverse direction also. Generally we have given. And then after giving the coordinate, kinematic independence, in how many ways it is a freedom I have identified first. So it is not having freedom at the fixed D. It is having rotational freedom at B, rotational freedom at C. So degree of kinematic indeterminacy 2. And then after knowing the degree of kinematic indeterminacy, I have indicated the coordinate numbers in the directions also. And then after giving that, fully restrained structure needed to be generated. Okay. Hence the fully restrained structure is as shown in the figure, simply indicating fixity at every joint. Whatever is the loading, only I should have to indicate, even though it is having roller and removing that, I should have to indicate fixity. This shades anyway you can give. Okay. This indication or this indication okay for any member. No problem at all. Okay. Just simply fixity or the complete restraint is there at the end. Okay, at the A, at B and at C the complete restraint is there. So after giving the fully restrained condition, what we should have to do? We should have to generate PL. Okay, due to this restrained condition, each member may have, or each coordinate may have some force. Okay, that load or the forces needed to be calculated. So for such type of fixed structure or the restrained structure, I am calculating the fixed end moments, because due to fixed, what is changing? Fixed moments are changing. So the developed forces due to the restraining, conditions are MFAB is equal to minus MFBA is equal to MFAB if it is clockwise, that is positive, and minus MFAB it is negative. So this is minus 60 into 4 square divided by 12. So MFAB is minus WL square by 12, MFBA is plus WL square by 12. See here. Minus WL square by 12 and plus WL square by 12. Okay. So in this way, minus WL square by 12 it is having, and I have given the formula with minus WL square by 12. So MFAB is equal to minus WL square by 12 and MFBA is plus WL square by 12. That's why it has having its own minus, and the value is minus 80 kilonewton per meter. So 80 kilonewton meter, W into 4 meter square, W 60 into 4 square by 12. And then for BC span, as the point load is there, MFBC is equal to minus MFCB is equal to minus WL by 8 and minus W into L by 8, and I have got the formulas. So these are the fixed end moments only. These are the fixed moments. Now I should have to generate PL loading vector. Okay, that PL loading vector, how can I say? So then the forces, generally forces, here only moments. Okay, forces, moments in this case developed in the coordinate directions due to the given loading. Firstly, at coordinate 1, due to the given loading, what is the fixed end moment or the moment? That is 80 . So this is the way we have got, right? Now this is coordinate 1, this is coordinate 2. So at coordinate 1, what is the force? This minus this, 80 minus 37.5. That is the final force developed at 1 due to the load. Okay, the force developed in the coordinate 1 direction. In the coordinate 1 direction, in this direction I have got, right? So 80 minus 37.5, in this coordinate direction the force developed is 80 minus 37.5, which is equal to 42.5. And then here in this direction, in the coordinate direction, the final force left is plus 37.5. So at the coordinate 2, the final direction in the coordinate direction is plus 37.5. Okay, so 42.5 and plus 37.5. And the above forces are positive if they act in the positive direction of the coordinate. Yes. So as the net result is in this direction and these two's net is also in this direction, that's why they are positive. If the coordinate is in this direction and the result I have got in the reverse direction, that should have to indicate in the negative. I have taken coordinates in this direction only. My assumption is also in this direction, and also I have got the outputs in this direction, that's why they are positive. So the PL vector was okay. Next, after knowing the PL vector, stiffness matrix needed to be generated. So the stiffness matrix, how we will generate? Now for the restrained structure, okay, so at the coordinates, in the coordinate direction, we will give 1 unit displacement. After getting PL load vector, then we should have to generate the stiffness matrix. How the stiffness matrix can be generated or given? So the stiffness matrix can be generated by applying unit displacement at the coordinate in the direction of the coordinate. Firstly, I am applying at for coordinate 1. Okay, so it is assembled using the slope deflection equations, and later is the process of stiffness matrix. Remember here, their conjugate beam method we have used. Here we are using stiffness matrix method. Okay, firstly, a unit displacement is applied in the unit coordinate direction 1. So in the direction of 1 unit of displacement is applied, that as that there the output is in moments, so I am applying 1 unit rotation. So at A it is still fixed, at B originally it is fixed, but a unit rotation theta is equal to 1 is applied, and the fixed has shifted like this, and the beam member was indicated like this. Okay, so stiffness at 1 due to rotation at 1, stiffness at 2 due to rotation at 1. K11, K21. Force developed at 1 due to unit rotation at 1. Force developed at 2 due to rotation at 1. So, K11 delta 1, what it is indicating? Due to delta 1 displacement, force developed at 1. Due to delta 2 displacement at 2, force developed at 1. And here 1 unit displacement. So, K11 into 1. So, due to unit displacement at 1, force developed at 1. Unit displacement at 1, force developed at 1. Unit displacement at 2, unit displacement at unit displacement at 1, force developed at 2. K21. Unit displacement at 1, the corresponding force developed at 2. Force developed at 2 due to the unit displacement at 1. Force developed at 1 due to the unit displacement at 1. So, K11 and K21 is indicated like that. And then, how we will calculate? Similarly, the next structure applying unit displacement in the coordinate direction 2. So, when keeping the remaining structure fixed, only applying unit rotation in the coordinate 2 direction. Again, in the same direction I am applying that theta is equal to 1 here. Okay. Now, K22. Unit displacement. Force developed at 2 due to unit displacement at 2. Force developed at 1 due to unit displacement at 2. K12, K22. Okay. So, force developed at 1 due to unit displacement at 2. Force developed at 2 due to unit displacement at 2. 1 radian of rotation is given to support C in the direction coordinate 2, and the forces or the moments developed in the coordinate direction are found. Okay. So, first case, applying 1 radian rotation at support B. Okay. So, simply I am giving the this was bent like this. So, due to unit rotation at B, force developed at B, force developed at C will be calculated, or coordinates, force developed in the coordinate direction 1, coordinate direction 2. Like that it is better, not at B and C. Force developed at coordinate 1, force developed at coordinate 2. Using the slope deflection equation. Remember, using slope deflection equation only. Now, K11. K11 is equal to, as this K11 is involving this span and this span. Okay. So, 2EI by L into 2 at B theta A minus sinking they have not even mentioned. Okay. And then 2E I by 3 theta C plus 2 theta B minus 0. Because at B towards A, here at B towards C, at B towards C, that's why where at comes there 2 times comes, towards the single time, 2EI by L, 2EI by length of the particular member into at which location I am doing, at B I am doing, so 2 times theta B, towards which I am doing A, so 2 times theta B plus theta A, and delta they have not even mentioned the problem, so that is equal to 0, and keeping that 2EI by 4 theta A plus theta B minus 0, and then for the next span 2EI by 3 into at B towards C, so 2 times theta B plus theta C minus 0, and here 4EI by 4, 4EI by 3, so 7EI by 3. In this way I have got K11 stiffness, force developed at 1 due to unit rotation at 1. Now force developed at 2 due to unit rotation at 1, that is K21. So K21 is equal to again 2EI by L. So here what is the force developed? K21, attitude due to 1, so 2EI by 3 into what is the thing here at C, so 2 times theta C plus theta B minus 0, 2 times theta C plus theta B minus 0, and theta C is 0, only theta B is 1, theta A and theta C are zeros only, so theta B is only 1, theta A and theta C are zeros, so substituting that, theta B is equal to 1 and theta C is equal to 0, so 2EI by 3, so that is 2EI by 3, K11, K attitude due to 1. Okay, next thing, application at the direction 2, due to the application at the direction 2, so such that as I am applying at the direction 2 only, K22 and K12. So attitude due to 2 EI by 3 into attitude due to 2, that is 2 theta C plus theta B minus 0, and here 2 EI by 3 theta B at B, so 2 times theta B plus theta C minus 0, theta C is 1, theta B is 0, theta B is 0, theta C is 1, so 4 EI by 3, so 2 times K12, 2EI by 3, 2 times theta B plus theta C minus 1, and it is 1, so that is 2EI by 3 only, as it is 2EI by 3, that is K12, and then K22, 2EI by 3, 2 times 3, that is 1, that's why 4EI by 3, so K22, that is 4EI by 3. Now keeping all the things in the stiffness matrix, and the final forces acting in the directions 1 and 2 are, so after knowing all the things, the complete C support, C end is 0, there is no moment, and at the B there is no support moment in the direction, because that will be equilibriumly maintained. So equilibrium maintenance is happened, so the net force is 0, as it is simply supported, there is no force for the moment there. Okay, the corresponding moment is not there. Okay, so P is equal to 0, 0, and then the stiffness matrix is equal to indicating 7EI by 3, 2EI by 3, 2EI by 3 and 4EI by 3. K11, K21, K12, K22, K21, and that is equal to delta 1, delta 2, and which is equal to P 0, 0 minus minus PL corresponding load values. Okay, and keeping that as it is, and multiplication of the taking the EI by 3 common, and 7, 2, 2, 4, and delta 1, delta 2, and as it is the right side section, and delta 2 will keep here, and keeping the delta 1, delta 2 here, and taking the remaining terms that way, so 3 over EI, and for this matrix inverse, so 7, 2, 2, 4 minus over minus 1, that is inverse, and keeping the as it is function. Same as we have already said, A, B, C, D inverse is 1 over AD minus BC, D minus B minus CA. So we are going for the highest of 2 by 2 only, because in our syllabus, the highest unknowns we should have to solve are 2 only. So 2 unknowns means 2 deltas or 2 forces. Okay, 2 delta answers. Okay, so delta 1 and delta 2, after the rearrangement, multiplication will get the output as 1 over ei minus 11.875. So delta 1, delta 2, this matrix is equal to 1 over ei times minus 11.875 minus 22.188. So these values we have done. Now knowing the individual deltas. So what the delta means? Delta is displacement in that particular coordinate direction. That is what the original rotation, right? So theta b is equal to minus 11.875 by a. Theta c is equal to minus 22.188 by a. So what this minus is indicating, and theta a is equal to 0 because of the fixed, since it is the fixed end. So once you know theta a, theta b and theta c and fixed end moments we know. So can we calculate the support moments using our original slope deflection method? Yes, we can calculate, because here I have thought of calculating theta b, theta c only. I am not even thinking about any other things. Okay, the support moments I am not at all thinking. Only thing is I am calculating inside theta values. Okay, so those theta values we have calculated. MAB is equal to minus MFAB, or original MFAB minus WL square by 12 plus 2 times theta A plus theta B. Theta A is 0, that's why theta B as it is I am writing 2EI by L, 2EI by L into 2 times only theta B. That answer. And then MFBA, so that is equal to plus WL square by 12 plus 2EI by L plus theta A into 2 times theta B. So 2 times theta B is coming. And then for MFBC is equal to again minus WL by 8. This is WL square by 12, WL square by 12, this is WL by 8, and 2EI by L into 2 times theta B plus theta C minus 0. 2 times theta B plus theta C. So here itself it is having minus, that's why as it is I am keeping, and the final output we have got like this. So in this way the final support moments are calculated. And finally, so any method will give us one way for analyzing the support moments only. Here also our method has given the analysis using the stiffness matrix, and the stiffness matrix has used the concept of slope deflection, so that we have given 1 unit rotation and the corresponding stiffness matrix we have generated. That stiffness matrix again has given me what is the displacement possible. Okay, so the background and bent. So due to unit displacement, what is the force developed? Due to the force developed, what is the deflection? So again the same rotation concept we came back, and finally we will complete the whole syllabus with this today's class. Thank you so much for the session. Thank you.